Okay, so let's continue on the lecture at here. Why is there only one screen showing? I don't want to mess up. Is it okay? Just one screen? Yeah. Okay. So. Let's continue on the review, and we'll finish the review today, okay, on the loading and stress analysis. Okay. In the first lecture, and I have talked about, okay, and okay. Yeah. Okay. In previous lecture, we reviewed on the causes of a different type of stresses, basically what type of normal and shear stress. And we also look at the general state of stress. To describe the general state of stress, Mohs circle is the best tools that you can rely on in order to find basically where the principal normal stress is and where the principal shear stress is. So here is just basically a quick note on the drawing of a Mohs circle. You draw a state of stress based on the loading condition, okay, and you have to rely on the sign conventions for drawing the Mohs circle very carefully, okay. So basically your positive tension is positive like this way, but the shear stress is treated as positive in the Mohs circle, slightly different. If it's causing it to go clockwise, then it's considered as a positive in the Mohs circle. If it's causing to go counterclockwise, then it's actually considered as a negative value in the Mohs circle. Okay, so that's something you have to be extremely careful there. But overall, the steps are quite simple, quite straightforward. Based on the state of stress, sigma x, tau xy, figure out where that coordinates representing this positive face out here. And then find the center of the circle, just draw the circle, and that's the Mohs circle. And this one here is the existing state of stress, right? So this is your current state of stress. And the Mohs circle tells us immediately that this is your principal normal stress at here, and this is your principal shear stress at here. So you can literally say, okay, I need to go counterclockwise from here to here, or to basically rotate this one by a certain degree to reach this state of principal normal stress. And how much degree? So from the Mohs circle, whatever the angle at here divided by 2, that's how much you would reorient or rotate to reach this principal normal stress. Okay? Yeah. So that's how you read it, this Mohs circles. We can also use this Mohs circle idea to explain actually quite a few different basically phenomena that are here. Okay, so maybe let's start with a very simple one, just exercise, basically exercise of drawing a Mohs circle, for example. So let's say we have a bar that is subjected to a bending on both ends. And the bending is basically, this is your z-axis. Okay, so the bending is this plane, the xy plane there. Okay. So now I want you to draw, let's say, based on this loading condition, what will be the Mohs circle? Or what will be as the state of stress, and then what will be the Mohs circle? Okay, based on the state of stress, like this, right? Yeah. Okay, so the steps that you always do is, you have to come up with a state of stress first. To come up with a state of stress, typically you would cut a cross section anywhere vertically. So cut it. Okay, so that's your orientation. You cut it vertically anywhere. So now if you look at the cross section after the cut, right? So this is the cross section after the cut. Okay, and we're interested, let's say, in of course, the location that give us the maximum value. And we learned in the previous lecture that the bending moment will give us bending normal stress, And in this case, the bottom here will experience tension, and the top one here will experience compression. So I'm going to take a stress element from the bottom and here. Okay, yeah. So taking a stress element from the bottom, and the way you take it, okay, is you start to draw a very small rectangle, okay, at that location. Okay, so and then at this location, of course, you would have a sigma x, okay, due to this bending moment. Okay, then you would extend that little rectangle, okay, extend the rectangle into a cube. Okay, so extend the rectangle into a cube. Okay, so this cube is basically the state of stress, okay, for that stress element. This cube is called stress element, and then you draw the state of stress on the cube, right? Yeah. So for this stress element, now to be in equilibrium, then you do need another sigma x on the other side of the cube, right? Yeah. And because there are only bending moments like this in this picture, so there's nothing else. So that's all the stress that you have for this stress element. Okay, and this is what we call, it's a planar stressed state of stress. Because why? Because if I look at it from the front, right? So if I look at the front view, so all we see is sigma x here and a sigma x at here, right? So that's the front view. This is called the planar state of stress, or plane state of stress. And the value of the sigma x, of course, equal to mc over I, right? That's it. Okay, that's the state of stress at here. And this is our face A, and this is our face B, right? Face A and face B. Okay. So now I'm ready to draw a mole circle based on this state of stress, okay, this stress element. First of all, you can write down the face A coordinates, which is sigma x 0, because there's no shear stress. So face B has a coordinate which is actually face B, what? It's a 0, 0, right? 0, 0. Okay. So to draw the mole circle, first draw the sigma and tau coordinate system, and find the coordinates for the A, so which is A at here. And in this case, is actually, you could also easily find the coordinates of B. Okay, coordinates B here. So that's it. And then you can form a circle, okay, with a radius of half of that. And that's your mole circle, right? Mole circle. Good. So based on this mole circle at here, and now we can maybe observe some very simple ones. And we say, okay, so where is the principal normal stress? And apparently it's this location, right? This is your principal normal stress. Okay, so this is your tau max at here. Okay. So here is your current state of stress. That is your current state of stress. So now, if somebody asks you is, okay, can you find out what is the orientation, or what orientation should I rotate so that we can achieve this principal shear stress from the current state of stress? So you see that, okay, I'm going to have to rotate from this A and to this location by how much angle rotation, as we just said? 45 degrees, right? So if this is your current state of stress, then you rotate, this is counterclockwise. So basically you will rotate this way by 45 degrees. Okay. So this is your original one at here, right? This is your original x, and now you're at slightly different coordinate x prime, 45 degrees at here. And at this location, you would have your maximum shear stress. So the maximum shear stress, this is the maximum here. So technically, if I use the convention here, positive at here corresponding to a clockwise rotation, right? Yeah. So that's your tau max value. Okay. Yeah. At the principal shear stress, the normal stress is not 0. Okay, the normal stress, there's still some normal stress, which is of course less than the sigma x. So there will still be a certain amount of normal stress at here. So you have a sigma x prime on that location. So that's the idea, huh? Yeah, that's an example showing you basically why, how the Mohs circle, how to interpret it. So let's look at another one here, okay? And I think I actually talked about this during the review of the first lecture. So let me show you the picture that okay. So there we go. So let's see. I'm going to show you this one here, okay? Give you a bar right here, and we'll subject the bar with a torsion. Okay? Subject the bar with a torsion here. So if you do this experiment, okay, and you'll find that if the bar is a ductile made of ductile material, let's say steel or something like that, then you'll see that the bar actually breaks like this. Okay? So basically, it breaks vertically to the bar, right? Yeah. And you see the twisting signs like this, right? Yeah. A twisting mark. Now, if the ductile material if the bar is made of a brittle material, and you'll see that it's actually break like this. Okay, breaks like this. Okay. So this is where we're going to try to explain basically why the bar breaks like this or this, given different material under this kind of a loading condition, right? So, and this can be explained using the Mohs circle at here. Okay, so let's take a look at this example here. Okay. Now, before we present this example here, there should be a common fact that you should know. Okay, the fact is this. If you have a ductile material, okay, and typically it will fail due to shear stress. And for brittle material, it will fail due to normal stress. Okay, yeah, that's a fact. Okay, so now let's get back to this experiment at here. Okay, I'm going to redraw the bar at here. So let's see. We have the bar at here, right? Yeah, and we're going to subject the bar to a torsional type of loading. Okay. So basically means we're going to, let's say, twist the bar this side like that, and this side, okay, like this. So let's twist the bar, load the bar like that. Okay. Okay, so given the loading condition now, and the next step, we want to draw the state of stress, okay, or the stress element based on the loading. As usual, what we can do is we can always cut a cross section anywhere. Okay, and then we look at take a stress element out of the cross section, right? Yeah. So in this case, it's a simple loading condition, so really it doesn't matter where you cut it. So what is just look at the front, this side here. We can just look at this this location here. Okay, yeah. And the nature of stress caused by the torsion, right? If you look at the cross section, it's basically there's only one shear stress caused by the torsion, right? As we learned before. So let's say I'm going to take a easy location. I'm going to use this location here. Okay, so I'm going to take a stress element from this location. So let's make a little bigger draw a circle right here. So I find sometimes some students having trouble to understand how to take a stress element. So here's what we're going to take. So we're going to take from this location. First, you draw a small rectangle or small square. Okay, draw a square over there. Okay, then you will draw the stress at that location. Okay, or on that rectangle or on that square location. Okay, so the torque goes this way, right? The torque goes this way. Okay, so then at this location, if I want to draw the shear stress, if you recall from the first lecture, so what direction will the shear stress pointing to at this location? Pointing up or pointing down? So you have a shear stress caused by the T, right? At this location and here. At this location. What should I draw? Should I have a shear stress going this way, or should I have a shear stress going this way? Down, right? Yeah, so it has to be in a consistent direction as the torque. Okay? So basically to create that stress element, you need to draw at this location, okay, draw that shear stress going down. Okay? Yeah. And then you can extend this stress element, okay, to a cube. Okay, a stress side to a cube. So that's a cube here. Then supplement this cube under the condition or assumption of equilibrium. So basically means you would have a shear stress pointing that way, okay, on this side here. And the other sides, they're all going to be empty, right? And also, of course, at the bottom and the other side, but you can, two sides is fine. Okay. Again, this is a planar state of stress. If I look at the front view, right, the front view will give us a state of stress, which is this. So technically speaking, of course, these two sides should supplement like that, right, to make it equilibrium. That's how you draw the state of stress, okay, and also the existing stress on the each sides. Okay. So technically speaking, this is your A sides, and this is your B sides, right? So you have A sides and you have B sides. And now I can draw the Mohs circle based on this state of stress. So here's the state of stress. Then what's the Mohs circle? So draw the sigma and the tau, and look at this simple state of stress at here. So A side does not have any shear stress, does not have any normal stress, only one shear stress at here, which will try to cause this cross section to go clockwise, right? So, and that, according to the Mohs circle convention, it actually corresponding to a positive or negative. Positive. So the A side have a 0 and tau value at here, right? And the B side has a 0 and a negative tau value at here. Okay. So now find out the coordinates for A and a B. So here's A, here's B. Then finish this with a circle connecting this here. So that's your Mohs circle. Okay, for based on this loading condition. The tau value, right? The tau at here. What's the tau value? The tau value, according to this first lecture, is what? T times R over J, right? So because that's at the edge of the bar, so that's your shear stress due to the torsion. Okay. So actually, this T times R over J, in this case at here, it happened to be what? Happened to be this is a special value, remember? This is called the principal shear stress, right? So in this case here, this is the principal shear stress, okay? Yeah. Okay, so now suppose that, okay, this is a steel bar, right? So this is a steel bar like this. If it is a steel bar, basically means it's a ductile material. Okay, so as we just said, the fact is the ductile material will fail due to normal stress, right? Yeah. So we need to look at basically at which cross section that the bar or the material will subject to the maximum normal stress, basically. Okay? Yeah. So in this case, we know that the principal normal stress is either here or here, right? Pardon me? Oh, I said shear stress? Oh, right. So sorry, let's consider this is a brittle. I actually meant for the brittle one here, right? So you're right. So this is okay. So let's look at the brittle one here, right? Okay. So as a matter of fact, if this is made of a ductile, and this is already the maximum shear stress, and this is the cross section where we just did is what cross section? It's a cross section perpendicular to the bar, right? So you can imagine how does it feel? It'll feel basically will break with the cross section that is perpendicular to the bar. That makes sense, right? But so let us consider this bar made of a brittle material here. Okay? Yeah. And then as I showed you here, so the brittle material feel like this, right? Yeah. So the question is why feel like this? Does that make sense? Yeah. So why does it feel like this? As we just said, brittle material will feel due to normal stress. So you look at this one here, where's the principal normal stress or maximum normal stress? And that's this location here, right? And this is the current state of stress. How do I go from existing one to the state where you have the principal normal stress? You got to go from here to here. That makes sense? Right? So go from here to here, meaning you rotate or you basically reorient the state of stress from here to here by what direction? This is a clockwise direction. And how much angle? 45. Okay? So reorient this one counterclockwise 45 degree. So which means if you do that, you get essentially a stress element, okay, more or less like that. So initially it's this, right? Initially it's this. And then you will do this 45 clockwise rotation up to this state. Okay? Yeah. That makes sense? So let's be careful with the sides here, right? See, your side A is over here. With a 45 degree rotation, where is my side A now? Side A is where? This is your side A here, right? This is your side A. And this is your side B. Okay? This is your side B. And what is the state of stress after 45 clockwise rotation then? At the side A location, at side A, okay, for this stress element, what do I exist? On side A, what kind of stress exists on side A? Side A, this is original side A, which is here, and now side A goes to this location. So what type of stress now exists on the side A? Normal, which is also what? Tensile, right? Let's call it sigma 1 here and sigma 2 here. Okay? Yeah. That make sense? So this is your tensile sigma 1. And what about the side? What about the B here? The B goes from here to here. So the B here also has a normal stress, but this is a compressive. Okay? That's your new state of stress with a 45 clockwise rotation. Yeah. And if you look at this location here, and that's basically what? This is basically like a cutting in this direction, right? You cut this direction, and that direction is perpendicular to what stress? To that normal stress sigma 1 here. Does that make sense? So we just said brittle material will feel due to the normal stress. And this is your maximum normal stress sigma 1 in here. And the cross section that is perpendicular to the sigma 1 is a cross section if you cut it this way, right? And or in other words, if you cut it 45 degree to this axis in this direction here. And that's why you see the break phenomena of this brittle material happen to be that way, right? Yeah. So another question to think about is a sort of unrelated. Now, if you are going to do is, if you're required to use a strain gauge to measure the strain, okay, to measure the strain of this bar, which is made of a brittle material, for example, okay, how would you attach this strain gauge to this bar surface, giving everything that we just described here? So you've got a strain gauge, right? Strain gauge. Let's see. If I use a piece of rectangle to represent the strain gauge. Strain gauge, you're learning measurement. So what does it give? It gives you the strain or deformation, right, of the sample right here. Okay. Yeah. So you want to get the maximum, basically, deformation right here. How would you attach this strain gauge to this loading condition to have the best information that you want? Yes?
90 degrees to the break, 45.
Exactly, right? So that's exactly what you want. Let me use maybe a green color here. So you want to attach the strain gauge to be 90 degree or perpendicular to the cross section that's going to break. Okay? Yeah. So that's the direction for the normal stress, and that's the direction of the strain, right? Yeah. Is that good? Yeah. So that's the usage of mode circle. Okay. Very useful. So in the first half of the class, actually, I do mention the mode, but you don't have actually many mode circle exercise. But if you have a skill of using mode circle, I think it's quite useful, in terms of better understanding what's going on, right? Okay. Okay. So now pretty much that's the review part. Okay. The other part I'm writing here, I don't think you learned yet. Okay. Wouldn't be a review, but it's a very natural extension, okay, from what we just reviewed here. So this part here, I call it 3D stress. Okay. And it's mode circle. Okay, 3D stress. So what I have presented here is basically what I mentioned. It's the planar state of stress. So you look at the front view, there's only stress exists on one side, right? And there's nothing exists on the front view or the back view side here, because that's planar. But in reality, 3D stress is really the most general state of stress, right? Yeah. So 3D stress essentially means you have all the 6 basically stress elements, okay, stress components exist on the cube, right? So if you draw a cube, okay, and you have all of the 6 that here exist on the cube. That's 3D stress, okay? That's 3D stress. Okay. So this is the most general one, right? This is the most general. We do need to actually look at the most general state of stress. Okay. However, we're going to look at it in a much simpler way, looking at it. Okay. But let's start with the general stage 3D stress. To have a 3D state of stress here, if you try to connect with the 2D state of stress, so 2D state of stress give you how many principal normal stress, for example? 2, right? Give you 2. So if you put it in a 3D, and naturally you will say, okay, so I got to have what? How many now? 3, right? Exactly. So when you have a 2D, you're just rotating in a 2D plane until a certain angle, and then you get the principal normal stress, right? Now when you have a 3D, then the rotation is not just in one plane. Could be actually, okay, rotate this way first, and then rotate that way, and then rotate this way, orientation, right? And then somehow, right? And at a certain state of orientation, and you will end up with basically principal normal stress. 3 principal normal stress. Okay, that's the nature of 3D, basically state of stress. Okay, so just bear in mind we will have 3 principal normal stress in 3D, and they are sigma 1, sigma 2, and sigma 3. Okay. And the convention is for 3D state of stress, you always order this basically 3 principal stresses like this way. So sorry, this is 2. So sigma 1, that is the greatest, and then sigma 2, and then the minimum sigma 3. Okay. Yeah. Okay. So how do we calculate the sigma 1, sigma 2, sigma 3 then? Or how do we know that which orientation that this sigma 1, sigma 2, sigma 3 going to be, right? So it's like a robotic hand. So here's the robotic hands here. And I can literally orient it to any different type of orientations, right? Yeah. So maybe at this location, at this orientation, then you have a sigma 1, sigma 2, sigma 3. Okay? Yeah. So the question is, how much is sigma 1, sigma 2, sigma 3? And at what direction the 3 normal stress are pointing to? That direction will give you this orientation, right, of this cube. So that's the 2 information that's tricky, that has to be answered when you have a 3D stress element. Okay? So the idea is basically, as I said, what does sigma 1 equal to, what does this equal to, what does this equal to, and the direction. Okay, the directions. So how do we find this out then? There is a very actually a useful way to find it out. So what you do is, okay, you form a 3x3 matrix. Okay, and this matrix is formed by like that. So sigma x, tau xy, tau xz. Okay, it's a symmetric matrix. Okay, you form a matrix, a 3x3 matrix, and this matrix, there's a terminology is called stress tensor, but it's okay if you don't remember that. So it's called stress tensor. Okay. Typically, if you are learning mechanics of material 2, this is something that you will come across again. Okay. Yeah. Now, when you actually, if you learn dynamics, I'm not sure if in dynamics there's also a similar matrix called what? Inertia tensor. Okay. Yeah. So when you have this 3x3 matrix, and now the linear algebra will come into the picture very handy. So when you have a 3x3 matrix, what can you solve for? You can solve for 2 informations. One is it's sorry? Anybody say something? One is called the eigenvalues, right? You can solve for the eigenvalues of 3x3 matrix. And for each eigenvalue, there's a so-called what? Eigenvector associated with that. So that is exactly the information we're looking for. So if you try to solve, let's say, the eigenvalue, basically what you try to solve is the roots of this matrix. So you can literally write as sigma times the unity matrix 3x3 minus this 3x3, and let it equal to 0, and calculate the determinant. You'll get the so-called eigenvalues. Okay? Yeah. So this solution of this one, okay, the solution of this one give us the eigenvalues. Okay? So you will have 3 eigenvalues. So actually, because the symmetric matrix is real, so you will have 3 distinct eigenvalues. And the 3 eigenvalues give you the sigma 1, sigma 2, sigma 3. Okay, so these are the three principal normal stress. And then you can calculate three eigenvectors, okay, corresponding to the three eigenvalues. So that'll give you the directions for sigma 1, sigma 2, and sigma 3. Because you got three vectors. The direction of the three vectors corresponding to this sigma 1, sigma 2, sigma 3 direction. Okay? Yeah. So that's the idea. I'm not going to go over into too much detail here, but that's the idea when you have a 3D Mohs circle, a 3D state of elements, and how do you get the three principal stress and the three eigenvectors for the directions. Okay? Yeah. So another thing, I'll show you animation shortly here. Okay. Another thing is for 2D you have a Mohs circle, and for 3D you also have actually a 3D Mohs circle. So very quickly to show you what the 3D Mohs circles is. Okay, 3D Mohs circle. What's the Mohs circle corresponding to a 3D state of stress, basically? Okay, very simple. You first find the three principal normal stresses. Okay, so find them by solving that, for example, the eigenvalues of the 3x3 matrix. And once you find them, and then you are ready to actually draw them 3D Mohs circle. Label each one of the sigma 1, sigma 2, and sigma 3 accordingly on the Mohs circles coordinate system. And then you can draw a circle between sigma 1 and sigma 2. Draw another circle between sigma 2 and sigma 3. And last one, you draw a circle between sigma 1 and sigma 3. So, three circles basically. The three circles represents the Mohs circles for these 3D elements. Okay? Yeah. And how you interpret it essentially is, so for example, if you have for example, if you have a sigma 1, 2, 3 like that, okay, yeah, then if you want to observe how the state of stress changes, so what you can do is, I'm going to rotate this stress element about sigma 1, okay. So basically, if you rotate about a sigma 1, then what you observe is you're going to observe there's a state of stress change in this circle here. If you rotate about sigma 2, and you're going to see a state of stress change in the sigma 1, sigma 3 here. Okay? Yeah. So I'll show you an animation here. Explorer. Okay. All right. So let's say, for example, right? We enter some values at here. So for sigma x, let's say we enter 100. Right. computer is not responding here. Okay, anyway, let me maybe try it next time, but it worked. It works offline, but somehow it didn't work. Whenever you want it to work, it doesn't work. So the idea is basically, it's just the observation of the change of state of stress whenever you rotate about a certain axis. Okay, yeah. But this is essentially the very basic about what a 3D stress is and what Mohs circles are associated with a 3D state of stress. Okay, yeah. Now in our case, okay, so in our case, what we do is, okay, so we typically, what we deal with planar state of stress. Okay. As you can see the examples that I showed you, whenever we have a loading condition, we typically will end up with a planar state of stress. So planar state of stress basically means your stress elements, your stress elements is looking like this. Okay, here's your stress elements, right? And which exist only in one plane, okay? In one plane. Okay. However, okay, for the design purpose, okay, for the general purpose, what we have to do is we're going to have to look at this state of stress, which is a planar state of stress, in a 3D sense. So what does that mean? Basically, is you would have to basically rotate this stress element and put it into a 3D sense. So here is still your x and y, right? Here's still the x and y here. And I'm going to basically now you're going to have to draw a stress element now, but it's a 3D stress element. So here's your xy plane. If you look at from the top, that should be what you see from here, right? Should be what you see it here. So basically, in this case, you will have a sigma x at here, and this is the tau xy. Okay, sigma x tau xy, and of course there should be this one here. There's sigma y at here. So that's what I mean by looking at a planar state of stress in 3D. Okay, so this is the key at here. Okay, so you need to look at the planar state of stress in 3D at here. Okay. So what this means is basically you're treating essentially this planar state of stress as if it's a 3D state of stress. Okay? But it's a much simplified 3D stress, because if I write that stress tensor using this planar state of stress, and all we see is here's a sigma x, tau xy, and 0 here, and tau xy, sigma y, 0, 0, 0. So this is your 3 by 3 matrix now, right? This is your 3 by 3 matrix. Okay. Yeah. And we can solve the eigenvalue of this 3 by 3 matrix, as I said, to obtain what are the 3 things we can obtain by solving the eigenvalues? To obtain what? The 3 principal normal stresses, right? Yeah. Now, because the nature there's a 0 at here, so the nature of 0 at here, you would get one of the solution is always 0. So basically, one of the principal stress will always 0, and the other 2, it's the same formula that we used for the principal normal stress. Okay, so that would be the solution, or basically that would be the eigenvalues for this 3 by 3 matrix. Okay. Now, once you get this answer here, then you can reorder the 3 values into sigma 1 greater than sigma 2 greater than sigma 3 to figure out which one is sigma 1, which one is sigma 2, and which one is sigma 3. Does that make sense? Okay. And I'll explain why do we have to look at the planar state of stress in 3D case. So why do we have to look at it in 3D case? I will finish that here, okay? We'll have to explain this from the 3D mole circle. Once you get the sigma 1, 2, 3 as the 3D mole circle, what do we do? We basically plot. But in this case, there's 1 and always it's a 0 at here. But let's just say you have a 3 here, okay? So here is your mole circle for 3D state of stress. Now, if you look at this mole circle for 3D state of stress, okay? Yeah. Where is that maximum shear stress? Where is the maximum shear stress based on the 3 mole circles? The 3 circles that are here, basically. Between, come again? You rotate this one here, basically you observe this circle here, right? And this is your maximum location, okay? If you look at the maximum location here, it's on which circle? On the circle formed between sigma 1 and sigma 3. Is that right? So basically what that tells you is this is a definite and additional information you would get if you would get, you know, if you don't look at it in 3D and looking at 2D only, then you would not have this information. Because if you look at 2D only, you may only have a look at this circle here. You know what I'm saying? So that circle may be actually corresponding to sigma A, sigma B, but that doesn't mean, right, your maximum shear stress is on that circle or on because the orientation. Okay? So that's why we have to look at a planar state of stress in 3D in order to figure out this information, the maximum shear stress. And that's the information that we need for the next step for static failure analysis. Okay? Yeah. Any questions? Oh, yes.
If one of them is 0, does the graph still look like the same?
It doesn't. So let's see if I draw this one of the 0 at here, right? And for example, right? For example, let's say this is your sigma A, this is your 0, this is your sigma B, for example. Okay, right? That's one scenario. That's actually we're going to look at a different scenario. So now you have your 0 at here, a sigma A at here, and sigma B somewhere here. So your 3 circle will look like this. Okay, right? So sigma A, sigma B, if you look at this one, this is basically that principal normal stress we analyzed when we look at the planar state of stress, right? So if you only look at sigma A, sigma, in this case, actually it generates the maximum based on sigma A, sigma B circle. But what about a different scenario? What about what if I have a sigma A at here greater than sigma B greater than 0? Basically, this is your sigma 1, sigma 2, sigma 3. And then what does that circle look like now? So sigma A here, sigma B here, and then 0 here. So you have a circle at here, circle at here. So this is your sigma 3, sigma A, sigma B, and then finally you have another circle over here, right? So now if you look at this maximum shear stress on which circle now? Between the sigma A and sigma 0, right? So, and the planar case, which is just sigma A, sigma B, that doesn't give you the maximum shear stress anymore.
So in the previous example, we got that one just by chance?
Yeah, this one is just kind of by chance.
Like in the 2D example?
2D. Oh, the example I'm giving it here?
I don't know, like
Further up. Yes, this is just by chance. This one here, actually, you look at this one here, this is exactly, see, this is a sigma A, sigma B, and a 0 at here. Right? Yeah. Is that good? So for design, we have to look at a planar state of stress. state of stress in 3D basically. Okay? Yeah. Any questions? All good? Okay. See you next week. Oh, sorry. Am I? Sorry. What time is the class anyway? We still got time, isn't it? Sorry. Yeah. When I have my first class, it's just totally screw me over here. Yeah. Got plenty of time. All right, so we're going to come back to this. It's good that you bring it up for now, okay? Yeah. Okay, so let's continue. That essentially finish all of the sort of prerequisites that we need for this course now, okay? Yeah. So let's go into what really we're looking for. Okay, let's look at the static failure first. And I'm going to look at we'll look at the static failure of ductile materials. Yeah, usually I'll see some sort of excitement when you see class is over, but this time nobody's so excited, so there's something wrong there. Okay. So static failure. First of all, what is static failure? And of course, static failure is because the failure under static loading. Okay, static loading. Static loading. When you say static loading, it means there is a stationary force. Okay, stationary force. So there's F applied at a different location on a bar, for example, or a stationary couple. Right. So there's a couple. Basically means the moment. So you have a moment applied to a bar like that. Right? Yeah. So stationary force or couple applied to a member, okay, to an object. So that's static loading. Okay? Yeah. And also I want to lay down some facts at first. Okay? So these facts basically they are sort of what you learn in material science, right? And we're talking about some facts for both ductile and brittle materials. Okay, so let me write down a few information right here. So what are the facts? Okay. First of all, for ductile material, and they are generally considered as failure when they yield. So the idea of the yield, essentially there's a permanent deformation or a strain will be caused by certain stress, right? Yeah, after the yielding point. And then brittle material, okay. Same thing. So they are going to be generally considered to fail when this time when they fracture. Okay. Yeah. So ductile material, you see some kind of a twist or deformation, but in the brittle material you basically see pieces in here and there, and that's fracture for brittle material. Okay. Yeah. So how do we differentiate between a ductile material and brittle material then? Right? We use this basically the strain at a fracture. This quantity to differentiate between this ductile and the brittle material. If this value is less than 5%, and this is basically a brittle material. For example, cast iron, right? That's a typical one. If this value is greater than 5%, then we consider this is a ductile material, okay? Like any carbon steels. It's another one. Yeah. And in this class, we also consider ductile material as the so-called even material. So we'll consider ductile material as even material. Even material meaning the SYT equal to SYC. So SYT is the tensile yield strength, and SYC is the compressive yield strength. So T is tensile, and C representing the compressive. And SY is the yield strength. So that's what the notation is here for. So for brittle material, our SY will be approximately the same as SU. So your yield strength is not much difference from the ultimate strength, which is the strength when it breaks or fractures. But your SUT is not the same as SUC. So basically, for brittle material, you also have an ultimate tensile strength and an ultimate compressive strength. So the U added here, ultimate. Typically, your SUC is greater than SUT for brittle material. So that's the fact for this class here. So it's not a fact for every ductile or every brittle, but this is for most of the time is true. Okay, so now let's get into the actual pictures. As I said, let's look at the static failure for ductile material. And we're going to present two different theories, or two different failure theories that's common for brittle material. So the first one, we're going to look at the so-called maximum shear stress theory. In short, I'll call it MSS. So first one, look at the MS theory. And the second one, we're going to look at a so-called distortion energy. I call it the DE theory. So we'll look at these two for ductile material. Those are important ones, especially for the second one. The first one here, there's in a textbook, and then you probably will see it could also be called Tresca theory. It's basically named after the people who proposed this MSS theory. So, and this is proposed in 1864. The second one, it's also named after the people who proposed it. It's called von Mises stress. And this is proposed in 1928, so fairly recent. Okay, so let's look at each one of the theory separately here, separately. But before I present this MS theory, so let's go back to that. Actually, let's go back to the statement, basically looking at the planar stress of planar state of stress in 3D. So let's go back to this here. I think we can summarize some of the information for our usage. So for planar state of stress in 3D, for planar in 3D. In 3D basically means we have three principal normal stresses. And as I just derived, when you have a planar state of stress, you look at it in 3D, you end up with one principal stress is 0. And the other two principal stress, which is obtained from the planar state of stress value, which is this one. Okay, that's your 3 principal normal stress, but we don't know at this stage, without the actual value of sigma x, sigma y, or tau xy, without these ones, we don't know which one is sigma 1, we don't know which one is sigma 2, and we don't know which one is sigma 3. Okay? But what we do know is you have to order the 3 values given at here according to the high to low. Okay? So that's how you have to do that. So that basically naturally brings us to 3 different cases now. Okay? 3 different cases. For a particular state of stress, you plug in sigma x, sigma y, you'll be able to get the sigma A and the sigma B. Then here are the 3 cases. If sigma A is greater than sigma B greater than 0, right? That's one possibility, right? So both of these values are greater than 0. Then if you look at the nature of the big to small, so the sigma 1 has to be sigma A, and sigma B, sigma 2 will be what? Sigma B, and sigma 3 is the 0 one. Okay? That's your first case. And second case, if sigma A greater than 0 greater than sigma B, so that basically gives us a different combination now. So sigma 2 is 0 and sigma 3 is sigma B. Because this combination will result in completely different calculation of shear stress, and basically which is plain from the 3D mode circles. And last case is if this 0 is greater than both sigma A and sigma B. Okay. So now your sigma 1 is 0 and sigma 2 is sigma A and sigma 3 sigma B. Okay. So that's the 3 cases. That's the maximum case that you could have. You might say, is it possible for sigma B to be greater than sigma A? It's not, because see the way you calculate sigma AB here, there's a positive, negative here. So the positive is always for A, negative for B. So sigma A is naturally greater than sigma B. Okay. Yeah. Okay. So we'll look at the 3 cases. Okay, when we look at each theory. Okay, especially for the MS theory. Okay. Now, there is also, if you're doing programming, okay, if you do programming, you can program like this to get your sigma 1. Okay, so basically sigma 1 is the maximum among the 3 quantities, and sigma 3 is the minimum among the 3 quantities. Okay, and you'll see this formula actually in some of the Excel that I give it to you for some future computations. Once you get sigma 1 and sigma 3, and you can calculate sigma 2 using this formula. So that'll you get a sigma 2. Okay? Yeah. In terms of programming. Alright. Alright, so now let's look at MS theory. Any questions so far? So let's look at MM theory. Maximum shear stress theory. I'll write down the definition first, and then we'll look at what this definition actually tells us. Okay. So the definition says failure occurs when the maximum shear stress in parts exceeds the shear stress in the tensile specimen at yield. Okay, so that's the MS theories. Okay, MS theory. So let you finish writing. So, if you look at this MS theory here, let's read it again in here, okay? So, we'll break it into pieces. Failure occurs when, first of all, the maximum shear stress in parts. So that's one quantity, basically, right? That's one quantity. And when this quantity, so I'm going to call this as tau max. Okay, so this is your maximum shear stress in the parts. Okay. Not sure how we obtain it yet, but that's what we're going to try to obtain, right? We're going to try to obtain a maximum shear stress. Exceeds what? Exceeds the shear stress in the tensile specimen at yield. Okay, so this is basically the second quantity. So when the first quantity is greater than the second quantity, and it's considered as fail. Is that clear? Right? And the second quantity here is called the shear stress in the tensile specimen at yield. This is basically, see, whenever, remember in the first lecture, when we talk about failure, in very simple language, is you always compare stress with what? Strain, right? So if the stress is greater than strain, it's failure. So basically, the second quantity here is the strains concept, and this is the notation-wise is essentially is the shear strength. Okay, so we're using SSY, the shear strength, the yield basically the shear for this quantity right here. So the idea is basically for MS is to compare two quantities, the tau max and the SSY. Okay, and of course we have to figure out what the tau max is, and we also have to figure out what this SSY is, right? Yeah. So for tau max, right, this is the maximum shear stress. I'm going to ignore any specific examples, but if I just consider, right, if I just consider a 3D, let's say, stress, if I just consider 3D stress, and as I just actually described, how do you describe a 3D stress using the Mohs circle? You basically draw three circles, isn't it, right? Draw three circles. And the three circles are based on sigma 1, sigma 2, and sigma 3. Okay? Yeah. So this is your 3D Mohs circle. And if you look at the 3D Mohs circle right here, where is the maximum shear stress? It's here. And that's the shear stress based on which circle? Based on the circle between 1 to 3. And this is your tau max. Basically, it doesn't matter what kind of a scenario you're dealing with. If you can ultimately put everything into this 3 circle, right, into this 3D circle right here, and you'll figure out the tau max based on the sigma 1, sigma 3 circle. And mathematically, the tau max, okay, it's actually basically equal to sigma 1 minus sigma 3 divided by 2. So when you have a circle and you have the coordinates for the diameters at the two ends, okay, and you can calculate the value of this, and essentially that's your radius at here. Okay, yeah. So your tau max quantity at here, it's basically sigma 1 minus sigma 3 over 2. So that's the formula for this. But of course, you need to ask. So what is sigma 1? What is sigma 3 then, right? And that has to be very specific now when it comes to individual questions. Okay. This one, no need to, because sigma 1 is always greater than sigma 3. Right. So this is a positive number. So you don't need to put absolute here, right? Yeah. So if you think about it, if I'm only looking at a planar state of stress, and then put in a 3D sense, So this is the three cases that we just summarized here, right? So now if you look at the three cases that are here, so this is where you will see three specific, examples. For the first one, here's your tau max, sigma A minus 0 divided 2. Second one, here's your tau max. Third one, here's your tau max. That makes sense, right? But overall, your tau max formula is this, okay? And based on this 3D Mohs circle set here. Okay, so that's your tau max. So we figure out the tau max now, right? We figure out the maximum shear stress. Okay, so we'll have to look at it in detail, of course. So now let's look at the SSY. Okay, we look at the SSY here. So basically, let's look at this is the first quantity, and then the second quantity at here is this yield strength in shear. Okay, SSY. So where this SSY from? If you read this language here, it's from a tensile specimen at yield. So that's where this is from. So this one here is from a tensile specimen at yield. Okay, that's the condition here. So we use basically every word that is given in this description, and the key is at yield, right? At yield. So you did experiments for tensile experiments in 259. So how do you do that? You basically apply force on both ends of the tensile specimen, right? Yeah. And then you observe when it starts to show the yielding phenomenon. And what we can do, in this case, I'm gonna take a stress element, cut it somewhere between, and then take a stress element, okay, and then draw the state of stress, and that's your basically sigma x. That's your state of stress, right? The state of stress here, okay. So if I draw a Mohs circle, okay, if I draw a Mohs circle based on this state of stress, so here's your state of stress. To draw the Mohs circle, basically, in this case here, your Mohs circle will be just a circle at here, right? Just a circle like this, because sigma y is 0, and there's no shear stress, and just this is your sigma x basically. Okay, yeah. Based on this Mohs circle and based on this based on this state of stress at here, it's actually very clear to you. You see, basically your sigma A equal to what? Sigma x, and your sigma B equal to 0. Okay? Yeah. So now, if you put this state of stress in 3D, so what's sigma 1? Is this, right? And then what's sigma 2? What's sigma 3? Exactly, right? So basically, you have a sigma A at here, and then at this location, it's your sigma 1, sigma 2 and 3. Okay? Yeah, sigma 2 and 3. So technically speaking, one of the circles shrink to the origin points, right? Yeah. So you only have one circle at here. Okay? Yeah. So now this is your Mohs circle, and then it says it's the tensile specimen at yield. So when the tensile specimen start to yield, what is the value of sigma x? At yield, what's the sigma x value? At the moment just about to yield, the sigma x has to equal to what? No. When the bar is just about to yield, not SSY, yield strength, SYT, right? Yeah. So when it's about to yield, your sigma x is basically reached the yield strength, right? The SYT. Okay. So that's the condition. You see, this is basically what it means: tensile specimen at yield. When the tensile specimen is about to yield, your sigma x equal to SYT. But what you're looking for is, it's not the yield strength, it's the yield strength in shear at that moment. What's the yield strength in shear? This is the yield strength in shear at that moment, right? That's the value. And what if sigma x equal to SYT, and then this value equal to what? The tau equal to, this is half of the diameter, which is 1/2 times SYT, right? So basically, the yield strength SSY at here equal to 1/2 SYT. Okay? Yeah. And the MS theory basically is asking you is compare this tau max, which is this, versus SSY, which is this. So that's what it basically is asking to compare. Compare this quantity with the other quantity. Okay? Yeah. And you can substitute this and this together, and you can see if sigma 1 minus sigma 3 greater than this, failure. Right? That's basically the idea. Okay? We'll look at the detail in the next lecture, breaking down to the case 1, 2, 3, and we'll draw diagrams trying to look at the safe region and unsafe region. Okay? Yeah. Any questions? Okay, this time is for real.